Now here's a handy equation. It's known as the heat equation. Basically what we have is the change in heat energy, which we'll measure in joules, equals mass in grams times the change in temperature in degrees Celsius times the specific heat capacity of the substance in question. Let's take a look at the units. Heat energy, the amount of thermal energy that flows into or out of a substance, is signified by delta Q in the equation. We'll measure in calories. Mass, which we'll signify with an M in the equation, we'll measure in grams. The change in temperature will be delta T. We'll measure that in degrees Celsius. Remember, that's how much the temperature either went up or down. And then the specific heat capacity, this is, think of it as a measure of how hard it is to change the temperature of 1 gram of a substance. So we signify it with a scary looking C, capital C, subscript P. Think of capacity. And the units are ugly. Calories per gram degrees Celsius. What this really means is, for instance, water has a specific heat capacity of 1. That means it takes 1 calorie to change the temperature of 1 gram by 1 degree Celsius. Now let's look at an example of how we'd use this equation. So we have a glass has a specific heat capacity of 2.2 calories per gram per degree Celsius. How much energy does it take to heat a 36-gram piece of glass from 20 degrees to 380 degrees? So what we're looking for here is how much energy. Always start by looking for the question word how much energy in this equation, delta Q, is heat energy. So this is what we're looking for. So what we'll have to do is substitute in for mass, delta T, and specific heat capacity. So let's just see what we've got here. The mass is 36 grams. The change in temperature, the delta T, is not 20 and not 380, but the difference between them. That's how much it changed. It actually changed by 380 minus 20. It changed by 360 degrees. Times however hard it is to change the temperature of glass. And it turns out that this unit is wrong, by the way. It's 0.22. I know that because water has a high specific heat capacity of any substance, and water specific heat capacity is 1. So this was written incorrectly. It should be 0.22 calorie gram per degree Celsius. So I'm going to put a 0.22 here. So all I have to do now to find delta Q, the amount of energy, is multiply through. So let's just take out my handy dandy calculator and enter these numbers. Here's how I'm going to do it. I'm going to say simply 36 times 360 times 0.22, and I find it takes 2851.2. Delta Q equals 2851.2. That would be in calories. But, well, look, I have in both cases I have 2 significant figures, so I'm going to round this to 2 significant figures. I'm going to keep this one, I'm going to keep this one. The 5, if it's 5 or more, you round this one up. So I'm going to write this down as 29, place holding zeros, calories equals the heat energy needed here. Let's take a look at another equation, another problem. Okay, in this case, what we have is, whoops, that's not right. Let's try another one. Okay. This is known as a calorimetry problem. What we have is a 17-gram piece of iron is taken out of a negative 25-degree freezer and put in 37 grams of water at 14 degrees Celsius. Both the water and the metal both end up at 12 degrees Celsius. You notice that the cold metal heated up and the warm water cooled down. So we want to know, what is the specific heat capacity of the iron? So what we're looking for is the specific heat capacity of the iron, which means I need to be able to substitute in the following information. Now, I know that the mass of the iron is 17 grams. I know that the change in temperature of the metal, it was negative 25 and it ended up being 12. The difference between those two is 37 degrees. I'm looking for the specific heat capacity, but I also have to know what the delta Q is. Now, in this case, I wasn't given either piece of information. I don't know what the delta Q is, but I can find it by using the water. And this is what we do in calorimetry problems all the time. We solve for the delta Q of the water, and then we use that for the delta Q of the material we put into the water. But the nice thing about water is water has a specific heat capacity of 1, so it's very easy to calculate this. So what I look at here is I see that the water, I have 37 grams of water. So I have 37 grams of water. It changed its temperature 2 degrees Celsius, and it has a specific heat capacity of 1. So what I get when I say 37 times, what is that, 74? Let's just see. 37 times 2, 74. So 74 calories is what I get here. However much energy the water lost, that's how much the metal gained. So I simply take the calories that the water lost and I put it in here. That's how we do calorimetry. Now I just had to solve for CP. So what I'll say is, well, I know that the metal required 74 calories in order to make 17 grams, change the temperature 37 degrees. I want to get CP by itself, so I have to undo what's being done to CP. It's being multiplied by this and multiplied by this, so therefore I will divide by both. I'm simply going to divide by that. If both sides are divided by 17 times 37, parentheses, that should work just fine. I know if I've done it right because the number I should come up with is going to be less than 1, because remember, water has a specific heat capacity of 1. So let's just try this. I'm going to say 74 divided by parentheses 17 times 37, close parentheses, enter, 0.1176. 0.1176, and we're going to round that to 2 significant figures. We're going to call that 0.12 equals the specific heat capacity of iron.